As for our go number 1, who proposed the heliocentric model? Again, these are supposed to be on page 8. Feel free to take pictures if you want to go at a slower pace, because we will go our usual pace today. 2, how do we prove that Earth is not at the center of our solar system? So what technologies, what things do we have now that can really show us that, hey, Earth's not in the middle, it's the sun? And then number 3, we've got what is retrograde? What is retrograde? Let's go ahead and take a look at those. Okay. So number 1, the name of the person you need to know about the heliocentric model is Nicholas Copernicus, right? Mainly know the last name, but we got to know also for our online test on this weekend, and this weekend coming up later this week, Friday. We've got to know like Brahe, there's Kepler, and then Galileo, right? Those were the main people there. And then number 2, our devices we have today, we have telescopes that can see that planets aren't moving around the Earth, they're moving around the sun. We've got satellites that can literally like film this happening, that show us footage of it happening, right? So satellites. And then lastly, retrograde motion, which was the first like definitive proof of this before all the technology was kind of innovated. So let's get into number 3 then. What exactly is retrograde? Retrograde is the way planets move from our perspective. So sometimes from our perspective, we can see planets look like they're moving backwards in their orbits, but they're not actually moving backwards. We're just orbiting at a faster speed than they are. So these planets will move backwards because our planet's moving slower than that planet. I mean, my bad. Our planet's moving faster than that. Remember, the planets that are closer to the sun move faster than the planets that are farther away. But for example, you've got, I think Venus is like a 90-day orbit, right? So really fast 3 months orbit. Whereas you've got, I think Neptune is like 180 something years, something like that. Maybe I could be closer now, maybe. So that's going to be the difference there for retrograde motion. They're not moving backwards. They're just moving slower, and we're getting past them in their orbit. Okay, let's move on to our table of contents. Again, this is just stuff we already saw. Last update for the table of contents, guys, is going to be pages 8 through 9. Solar system formation, pages 8 through 9. Solar system formation. Give you guys a moment. So we're looking at, to be specific, how the stars formed and how the planets formed, right? Okay, let's do our first question of the day. Again, please answer in the chat, keeping things at a fast pace today. What 2 elements primarily make up most of the sun? Again, this will probably be on your online test on Friday. A, hydrogen and iron. B, helium and nitrogen. C, hydrogen and nitrogen, or D, hydrogen and helium? Please answer in the chat for participation. Please answer in the chat. Thank you, Michaela. Again, what 2 elements make up most of the sun? Got to know this. This will be a test question. Thank you, Diego. Thank you, Sanaya. Okay, take about 10 seconds. Still need more people. Thank you, Joseph. 5 seconds, 5 seconds. Need more people, need more people. Okay, let's go. Thank you, Daniela. All right, shout outs to Daniela, Joseph, Sanaya, Diego, and Michaela. That's everybody, yeah. The answer is going to be hydrogen and helium. Fantastic job, hydrogen and helium. Keep in mind there's a lot more hydrogen than helium, and eventually when the hydrogen runs out in a few billion years, that's when the star will begin to die, okay? Speaking of which, we know how stars die. They can either explode into a supernova, or like our star, the sun will probably end, like I said, in a couple 5 to 6 billion years, a long time, no worries. It is supposed to potentially expand into a red giant and consume the inner planets, even maybe Earth. But then it will, the outer layers of it will be shed, and all that will be left over is the core the white core, which we call white dwarf, right? A white dwarf star. So we have giant stars, dwarf stars. So that's going to be, it's going to just kind of like a light bulb fizzle out for the most part. So I want us to know then for our let's see. For our only video question today on page 8, how do stars form? Again, number 1, what do stars form from? And number 2, how do then planets form? So talk about how stars end, but today I want to know how stars start and how do their planets form as well. So give you a moment for that. Take a picture of that. That's going to go to page 8. And let's go ahead and check out what our answer. Just going to play a 2-minute video, guys. Again, how do stars form? And secondly, how do their planets form? Oh, we got an ad. Hold up. Music. All right. Sorry about that.
Hanging from Orion's belt in the blade of the hunter's sword is a jeweled cloud known as the Orion Nebula. Space here is littered with small globs of gas and dust. These are protostars, baby stars in the making, stellar cocoons, cosmic tadpoles. They form in galactic nurseries like Orion from clouds of gas and dust mingled with the ashes of earlier stars that have died and exploded. But like all newborns, the young star faces a perilous future. Buried inside this dusty cocoon, where astronomers can't see with regular telescopes, a secret star is being born. As the baby star tries to burn its way out of the cloudy egg that sheltered and birthed it, radiation from powerful stars nearby eats away the cocoon from the outside. Too much outside radiation can burn away not just the cocoon, but the disk around the new star, leaving the star naked and alone. If the disk survives, it could make planets, first by electrical forces as particles randomly collide and stick, then by gravity as clumps attract each other. As a planet forms, it will scour its orbit of dust, leaving a telltale gap like the grooves in a record. Recently, astronomers using the new ALMA radio telescope have made the most detailed picture yet of what might be planets being born. They found dark grooves scoring a disk around a star known as HL Tauri, some 450 light years from here. The disk is about 22 billion miles across, about 4 times the size of the realm of the planets in our own solar system. Are these gaps sheltering planets? Are we seeing the curtain rising on a new set of worlds like our own? HL Tauri is only 1 million years old, a blink in the long lifetime of a star. For a newborn sun, every grain of dust is a promise. It's morning in the Milky Way. Everything is still possible.
All right, so really, really cool stuff there, kind of showing us the beginning of life for a star in space. And as you saw for number 1, space isn't just an empty place of darkness, right? There's a lot of stuff in between the stars. That stuff being, for number 1, space dust and gas. And where we get that space dust from now, obviously we know hydrogen and helium, those are the 2 key elements, the key ingredients. But the dust itself comes from other stars that have died and have exploded, essentially. And when they explode, they leave a bunch of debris, okay? So then where does that leave our planets? Well, the planets, okay, they are going to be collected from the debris and the rock that's left over after that dust gets making the star. So all the tough stuff that is able to withstand the heat of the star and the sun is going to be what makes the planets. So kind of separating like different oils in a vial, that's how we're going to have the deviating difference in our planets, right? Okay. So again, space dust and gas for the stars, and the debris and rock for the planets. So let's move on to our main stuff. Dennis got 3 things to show you guys today. We'll do one more question. Again, we don't have fill in the blank sheet, so I'm just going to have you take all the write down all of this, and I'll put check marks for those who like to see that. Okay, so this is kind of walking you through the step by step, right? So first, we just get a regular old space cloud, right? Okay, so there's a bunch of dust and stuff in between all the stars. That's what ignites and creates our baby stars, right? Then, okay, you're going to need, like I said, mostly hydrogen and helium. You get a lot of other types of space dust and clouds, but it doesn't have a lot of hydrogen or helium. You're not likely to get a star from that, okay? So elements and dust, hydrogen and helium. If you guys want to take pictures, you can. We're going to move on here in 5 seconds. So start out with a cloud. There's a bunch of stuff sitting around in space. Next, we've got this picture, which is a really great picture. Walks you through what happens each way, step by step. All right, so basically you get your dust cloud, your space dust cloud, and over time, it's going to get more compact. It's going to condense. So what's going to happen to that cloud is it is going to start to rotate. It's going to start to spin. And when it spins, it's when you're really going to see a concentration occur that forms the cloud into like a disc, right? Like a frisbee. So it's spinning like a frisbee. And after it spins, it's going to cause that hydrogen and helium to ignite like a match and form our first baby star. Okay? So we're going to cause it to concentrate and form our first our star, right? Okay, so you guys see that? All right, before we finish up for the day, let's do our last question. Okay, again, last question of the day, guys. Listen closely, make sure to answer in the chat. What process helps power the sun? You should know this will definitely be a test question on Friday as well. A, nuclear fission. B, nuclear fusion. C, photosynthesis. Or D, solar magnetism. Please answer in the chat. Thank you, Lakia. Again, what process keeps the star and the sun strong for billions of years? Sanaya, thank you. A, B, C, or D? A, B, C, or D? Okay, go ahead, guys. Got 10 seconds. 10 seconds. Please answer for your participation. Thank you, Sanaya. Thank you, Diego. All right, Irina, thank you. Joseph. 3, 2, 1, 0. Okay, so let's check it out. The answer is going to be shout outs to Joseph, Irina, Diego, Sanaya, Michaela, Lakia. Shout outs to you guys. Great job. Got it right. It's going to be B, nuclear fusion. B, nuclear fusion, fusing hydrogen and helium together. All right, let's finish up. Last notes of the day. We've got this here. Okay, so then as we get the cloud becoming a disk, it's going to collapse. And when it does, it's going to move faster and faster, and it's going to push everything to the middle of that disk. Okay, we call that middle force, super important, centripetal force. Okay, it's going to push everything kind of to the middle, and it's going to, like I said, it's going to kind of, after it ignites, it's going to burn up all the weak gases and all the weak rock, but it's going to keep all the tough, strong stuff. That's going to clump up together and concentrate to form our planets. Okay, so again, it's going to be a rotating disk. clumps together, gets stronger, okay, at the center, caused by centripetal force and the rotation of that cloud that becomes a disk and then a star and a set of planets. All right, so that concludes what we got for today, guys. Let me go ahead and just show you real quick again. Just as a reminder, we've got the vocab. If you haven't already finished that, guys, that's going to be due on that's been due since last Friday, but if you want to be on it, so you can still turn it in. And then we've got these article questions, right? So you got to go on Canvas, finish reading the articles. For article 1, you've got to answer questions on the satellites, as well as how we work with those satellites when they get disrupted. Number 2, we look at auroras and solar wind. And then number 3, solar storms and weather. All right, guys, let me go and take attendance here.